All right, AP Chem, here are your answers for the most missed questions on review number 4. This particular question asks you to do net ionic equations, and there were a couple that asked net ionic equations that many of you missed. So I'm going to walk through the concepts of a net ionic equation for you. You want to write the actual chemical equation, and then anything that's aqueous that actually dissolves in water and soluble can split up into ions, and you can cancel those on both sides. But you want to be careful with this. This is the addition of a weak acid. Weak acids, we know, do not 100% ionize. It's a very small percent ionization. And that means that it's going to stay as aqueous, stuck together. It's not going to make the ions, even though it says aqueous in the chemical reaction. So if you look at your chemical reaction here, B, let's go down to our, let me find it right here, our bottom one right here. E, this is what it would look like as a double displacement reaction. This will be your molecular equation. The hydroxide would attach to your two H's and make two H2O's, and then the barium would attach to this sulfite ion. And you want to break up everything that's soluble. Well, barium hydroxide is a strong base. It's soluble. So this would make the barium ion and the hydroxide ion just like this. And the barium sulfate is insoluble. It'd stick together. And the H2O can't break apart either. It has to stay stuck together. So if you look at this equation and you separate the only thing that can separate, which is this right here, you get the net ionic equation in B right here. And the reason you can't cancel anything is because there's no ions on the product side. Everything's the solid and liquid stays stuck together. Okay. Let's look at another net ionic equation. The reaction between sodium fluoride and hydrochloric acid. Your molecular equation would be given to you in A right here. Sodium fluoride, hydrochloric acid, double displacement. The chlorine goes to the sodium, and the hydrogen goes to fluorine. Well, this is a weak acid, and weak acid stays stuck together. So it's not going to make ions in solution, but this will make ions in solution. This is a strong acid, so it'll break up, make ions, and this will make ions in solution. So what would that look like? Well, it'd look like B here. If you make, so this is a molecular equation. B would be the complete ionic equation. And then you can cancel everything. That's what net ionic is. Cancel everything that's the same on both sides. So sodium would cancel with sodium. The chlorine would cancel with the chlorine. And the only thing that's left would be H plus and F minus to make HF. And that's what the correct answer is. It's D. Our next one, you have lithium in an Erlenmeyer flask, and it reacts with H2O. After all the lithium has reacted, the solution in the flask is added to clean diburette and is titrated. But they just ask a simple question here: what's the following balanced? Which of the following is a balanced net ionic equation for the reaction between lithium and water? What happens when lithium and water interact with each other? Well, lithium will steal your hydroxides. So it'll steal the O and the H and leave one H out on its own to make H2 gas, and you get B for your answer. You probably wouldn't have a question like that on this year's test. Which of the following piece of labware should be used to most accurately measure out 25 milliliters? You might have a question like this on the test. Pipettes are for measuring really small volumes, so B is your correct answer. It's the best at measuring that. You would not want to use a beaker. We never use beakers to measure volumes. We use beakers to collect volumes, so you dump them in after they're measured. Erlenmeyer flask, again, you don't ever use an Erlenmeyer flask. They're shaped like this to measure a volume. Graduated cylinders, we do use this to measure a volume, but if there's a more precise device, which there is in this case, the pipette, more precise than a graduated cylinder, that's what you would use. Just a couple other pieces of glassware. Burette is what you'd use for a titration, and that's your long, thin glass with multiple marks all the way down. We use these for titrations. It's spelled like this to deliver volumes. And that's pretty much all you're going to see for reactions. If you're making a solution, you'll use a volumetric flask, and volumetric flasks look like this. They're round bottom instead of the triangular one of an Erlenmeyer flask. It only has one mark on it. It's only good for measuring that one volume, and this would be used for making solutions or dilutions. Our next problem, survival aquatic organisms depends on the amount of O2 that's dissolved in H2O. You've got some diagrams up here, and they ask you which diagram's better at representing what actually happens to O2 when it dissolves in water. Well, the first thing you want to recognize is H2O is polar. We have a negative side and a positive side. And then our O2 molecule is nonpolar. The charges are the same on both sides. And if it's a nonpolar molecule trying to dissolve in a polar, you can't have a hydrogen bond. That's what's represented here. Some of you might have chosen this because you see the OH with the negative electrons on it, and you think, oh, hydrogen bonding. But a hydrogen bond has to be between an oxygen, nitrogen, or fluorine that's attached to hydrogen in the compound. And that allows for a really positive hydrogen and a really negative oxygen. And we don't have that because this O2 molecule does not have a hydrogen in it. So it can't hydrogen bond there. So let's look at our answers here. The diagram 2 is the correct answer. The nonpolar molecule will get an instantaneous dipole created as that electron cloud shifts. So if positive hydrogens got next to it on this side, the electrons would shift towards the positive hydrogens, and that would make this nonpolar molecule slightly negative on this side. The cloud would shift, and slightly positive on this side, and the oxygens would be attracted on the other side. So our correct answer is diagram 2. You can't do hydrogen bonds with it. That's why A is not correct. They're polar molecules. This is not polar, so that's not correct. Diagram 2, because the polar H2O molecules can create a temporary dipole. That's your correct answer. Spectrophotometry. This is a Beer's Law problem. And just to refresh you with this problem, a student measures all of these samples, 4 different samples, and they put it in a colorimeter and measure the absorbance values. And they're asking what's the most likely explanation for the discrepant data in trial number 4. Well, trial number 4, why is this discrepant data? Let's look at that first. This doubles in concentration, and Beer's Law says that your concentration depends, or your absorbance depends on your concentration directly. So if concentration doubles, you're going to have an increase in absorbance on this side. And it looks like it about doubles, or just over doubles. If we go here, it doubles, and it just about doubles on this side as well. And then from here to here, it's not a double, it's a 50% increase. And a 50% increase, what would we expect here? What's 50% of 0.5? Well, that's approximately 0.25. If we just do some rough math, 0.52 plus 0.25, we'd be close to what? 0.7, 0.70 is what we should get here. So we're way too low for absorbance. This absorbance value should be a lot higher. Why wouldn't it be as high? Let's look. The solution was at lower temperature. No, temperature is not going to impact it. The measurement was made using a different spectrophotometer with a cell with a longer path length. Well, a longer path length, if we have a short path length, compare that to a long path length with the cuvette, the long path length is going to have more light absorbed, and we get a larger absorbance value. We have a smaller absorbance value, so B is not correct. The solution was saturated, and the flow of light through solution was restricted. No, that would increase our absorbance as well. So D is our only correct answer here. The concentration was actually lower. And if the concentration was lower here, we would expect a lower value for absorbance, and that would match our discrepant event. A 0.2 mole sample of magnesium chloride and a 0.1 mole sample of calcium chloride are dissolved in water and diluted to 500 milliliters. What's the concentration? We want to know how many moles of chlorine are produced. So magnesium chloride would separate out into 1 magnesium and 2 chlorines. And you want to know how many moles of this are produced. Well, if we have 0.2 moles of this, we're going to produce twice as much, 2-to-1 ratio at 0.4 moles. And then we do the same thing for potassium, KCl. Well, that's going to dissolve and make potassium with a +1 charge and chlorine with a -1. And we have 0.1 moles of this. So we're going to end up producing 0.1 moles of this. It's a 1-to-1 ratio. So what's that? Total, we have a total of 0.5 moles in our container. Our volume is 0.500 liters. That's our 500 milliliters. So 0.5 divided by 0.5 gives us an answer of 1 molar. And that's it for this particular set of problems.